Okay, it's the top of the hour. Hi, my name is John Kingham, and I'm the host and presenter for today's webinar. I've been working for Bentley, Nevada for the past 34 years. I started in our Machinery Diagnostic Services department and traveled the US and the world diagnosing machinery based upon their vibration characteristics. The past decade or so, I have been working as an application and solutions architect. And in this role, I help our customers develop condition monitoring and protection solutions for their plants. We are recording today's session. In order to make these videos worthwhile to you and your colleagues, we do ask that you make sure that you are on mute and refrain from broadcasting your video. And we are using the Slido app right over here at www.sli.do. So when you go in there, use Bentley KPH as your user ID. I always find it's helpful to vote on your own question, gives it a little extra priority. Even if you aren't asking a question, you can vote on questions to make it go up to the top of the queue. But as we are recording, we will wait until the end after we stop the recording to pose and answer the questions in the queue. So with that, I'm going to go ahead and start and talk about everything you ever wanted to know about Keyphasors. Well, first of all, let's define what a Keyphasor is. Right, so a Keyphasor is typically going to be a proximity probe that's viewing a notch or a projection, and it's going to give you a once per turn event. If you have more than one per turn, it's really not going to be as effective. So here shows as the notch goes by, you get a negative going pulse. Here, as a projection goes by, you get a positive going pulse. And here's real world Keyphasor. So you can see that there is a little bit of vibration on that signal, but the majority and what we're going to be looking at is that pulse. Okay. So I've been using this slide for a long time, and it has one issue, or I have one issue with it. That is, it shows a 50 mil gap here. You know, the gap is shown as 50 mils, but it is common to gap Keyphasors a little bit tighter at about 35 mils. This brings that DC voltage down to 7.5, so that when you get that pulse and it goes more negative, you get a bigger pulse. It optimizes that pulse. Okay. And we'll talk about this one in a little bit, but that's a projection. So what is the value of a Keyphasor, and why do we care? So phase angle is a big reason why we care, because we're going to filter the vibration at the 1 times running speed. We're going to use the 1x amplitude and the phase for things like balancing. Rotor diagnostics, we're going to be looking for resonances on startups and shutdowns. We'll also notice that misalignment. That's more of a steady state reading, but if you have a 180-degree phase shift across your coupling, that's a good indication that you have misalignment. And then precession. So which way is the vibration moving? Is it going in the same direction as the shaft rotation? If it is, that's called forward precession. If it's going backwards, it's called backwards precession, oddly enough. And of course, that can be caused by miswiring. So you've got to be careful of that when you see that. But a real severe misalignment can cause reverse precession. Overspeed is another thing that value of a Keyphasor. Zero speed, reverse rotation, and rotor acceleration. A couple of these things we'll go through. You'll find that you need more than one probe, but for the most part, a Keyphasor is a single probe. So let's talk about phase angle. The phase angle is defined as the number of degrees from the Keyphasor pulse to the first positive peak of vibration. That positive peak right here is a high spot, what you often hear as the high spot. Okay, so here we have Keyphasor pulse and Keyphasor pulse. So we have one notch. We know that that's 360 degrees of rotation in between these two. You'll also, I want you to notice that there's a blank spot and a bright spot. And back when I started, we used to use these old-fashioned instruments called oscilloscopes. I love an oscilloscope. It's a great tool. So we had specially modified Bentley, Nevada versions of a Tektronix oscilloscope, and it had both an X and a Y, and then it had an ability to put in a Z-axis, and that Z-axis was your Keyphasor. And when you were looking at your time base on the oscilloscope, and that pulse would come down, the voltage feeding into the oscilloscope would drop, and you'd get this blank spot. And then as the Keyphasor pulse came back, it would give you this bright spot. So when we look at a time-based waveform, we know that the blank comes before the bright. And that's going to be important on the next slide where I show you an orbit. So getting back to phase, again, we say it's defined as a number of degrees from the Keyphasor pulse. So from right here to this first positive peak. Okay. And because this is 1x, there is no other positive peak. That's the only positive peak we're going to see. So we go from here to here. We know from here to here is 360 degrees. So if we were in a seminar where you could raise your hands, I'd say, you know, how many degrees is that? So I want you to think about that. I'm going to guess it's probably between 30 and 40 degrees. So if we get to the question and answer section and you want to dispute that, we can do that. Okay. So here is an orbit plot with a Keyphasor, and I've kind of enlarged this so that you can see that blank spot and the bright spot. And you can see, so we are going counterclockwise, and somebody else has put this arrow in here. Now that arrow indicates the machine is going counterclockwise, and that was done in the configuration process of the software. I don't know if this is Adre or System 1, but we identified the machine as going counterclockwise. That could be, you might want to verify that, right? But in any case, the vibration is going in the same direction as the machine, so it's forward precessing. Okay. So here's I've got some other orbits in here because everybody loves orbits, at least I do. And here we have half X, and it's a suspected looseness. So why would it be a looseness? And why would it lock into half X? Hopefully, you know a little bit about rotor dynamics and understand that the resonance speed is going to be defined as the square root of the stiffness divided by mass. And so the mass very rarely changes, but the stiffness does. And if it's loose, it's going to be less. So here we had a resonance that was above half running speed. The looseness allowed that stiffness to decrease enough that the resonance became half of running speed. And I see a Keyphasor dot here and a Keyphasor dot here, and I apologize I didn't circle them. But if I was looking at this on an oscilloscope, it would be pretty steady, you know, but the orbit size is jiggling a bit. I also know that this is exactly half X because I can run a line between these Keyphasor dots. So, and they're parallel, and you'll see in another orbit time base, I think the next slide actually, that It's not half X. And I could do it down here. This is the opposite end of the machine, and it's still showing some half X from this bearing being loose. And I know it's this bearing because it's got a higher amplitudes than this bearing. Plus it is showing the classic loose orbit. Here I've got a orbit of an oil whirl situation. We've got multiple Keyphasors. So since I have multiple Keyphasors, I know it's not locked into, you know, a 1x or a half X or something like that. I go over here and I can look. I have a Keyphasor here, 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 here. I can't draw any lines that go straight through those. The other thing I'll point out is I've got my Keyphasor here. I've got a peak. I come down, I have another Keyphasor. So that's one revolution of the shaft. I come down, I have another peak, or not peak, Keyphasor. That's another revolution of the shaft. I get up here, and I've had another revolution of the shaft before I get to another peak. So it is something like every 2.5 revolutions, I'm getting a peak. So obviously less than half X, and that's a characteristic of oil whirl. So that's how I know that is oil whirl. Now here's another interesting one. Looks like a rub to me. You note the multiple Keyphasor dots. They indicate that this is not locked into an exact submultiple like half X or 1/3 X. And also notice that you've got kind of a squared off pattern right here in the lower left. It appears to hit something and rebound off of it. After this straight section of travel, it kind of regains its regular orbit path. And that's part of what you learn from looking at orbits. Now, if we turn to this cascade plot is made either during a startup or a shutdown. And you'll see that this is the running speed components. You'll see it says 1x up here. And right around 1200 or about 20 hertz, there appears to be a resonance. There's a peak here, right? And now note that once the rotor starts impacting or rubbing, it rings that frequency. And that's why we always look for horizontal and vertical relationships in cascades. You'll also see some 2x and some 3x of that 1200 CP or 1200 CPM frequency. And I think that's due to the squaring off, because square waves often give you those 2 and 3x multiples. Okay, so that's that. I told you that we use Keyphasors to help us do balancing, right? So this is a polar plot. Again, the polar plot is a 1x amplitude and phase versus speed in polar coordinates. So this is a shutdown or a startup. And right here, we're at low speed. So we're below the resonance. And below the resonance, the heavy spot is the high spot, okay? So if you can remember back to when you were a kid and you took a pail of water and you rotated it around, and again, if I was at a seminar, you could see what I was doing, but I'm moving my arm around and around. You'd know that water isn't going to come out of the pail when you reach the top, because you've got centrifugal motion going. And what's that centrifugal motion doing to your arm? It's pulling it, right? And so when you're below the resonance, that heavy spot is pulling the rotor. And that's why you go towards the heavy spot and the high spot are the same. You go through the resonance, and the way the math works, and you ought to take one of our machinery diagnostics courses, goes right through the math. You'll find that above the resonance, the acceleration term takes over. Acceleration is 180 degrees out of phase. So the heavy spot and the high spot are opposite of each other. So my high spot's over here, tells me my heavy spot's in the same spot. So I use that to do my balancing. I'm going to put my trial weight here. And if let's just say my Keyphasor is right here, I line up the 0 spot of the Keyphasor, that notch, right up here, and I walk over and I put my weight here. So it gives me a good physical location that I can reference as well. Okay. So that's a polar plot. Here's a Bode plot again, 1x amplitude and phase, different coordinates, x and y versus the polar. But it shows me I've got my resonance around 1500 RPM here. Shows me my phase roll off. Not as intuitive for balancing, but it does give you some good information. The other thing I always like to do on these is I'll put the direct measurement on here as well, because if you have something that's not happening at 1x, you'll pick it up here very easily. Okay, so that's why we want to use a Keyphasor. Let's talk a little bit about some of the design considerations. So again, we've got this photo, and I didn't mention it before, but a notch is preferred over projection due to how easy it is to gap and the probability of probe damage with a projection. If you think about it, it's very difficult to get this probe into this hole. It's just probably not going to even fit. But when you have a projection and you go to gap it, I'm going to say 90% of the time, if you're not thinking about it, probably even more than 90% of the time, if you're not thinking about it, this projection is not going to be right underneath that Keyphasor. So you're going to end up gapping it on the shaft itself. And the first revolution of the startup is going to wipe that probe out. We get to sell you another probe, but we would much rather have you get the information that probe's going to give you than the $150 for a new probe. It's just not worth it. So best bet, design it so that you have a notch. And while we're at it, let's talk about how to install that notch, right? So we're going to mill that notch in using a 3/4 inch ball end mill. This ball end mill obviously is going to create a spherical shape, and that reduces those sharp corners, which cause stress concentrations. You can imagine, here's a sharp corner, here's a sharp corner, another sharp corner. If you're going to get any shaft cracks, it's going to propagate at these sharp corners. So using a ball end mill is going to reduce that. Okay. And don't worry so much about the width of the notch. That's going to be dictated by the depth of the notch. And we want the depth to be between 6/1000 and 6/100 and 1/10 of an inch. And if you think about it, the range for an 8mm prox probe is about 80 mils, which fits right in between those two. Again, and if you're pulling it out 35 mils, you're really only using maybe 50 mils of that range. So it doesn't have to be that deep. And then what about the length of the notch? Okay, and that depends upon your expected thermal growth. So if you're putting the notch in near the collar, the thrust collar, you're not going to get much thermal growth, and you can just dimple that shaft. Just make sure that the dimple is put underneath the probe. And as far as if you need to put some length into it because you're away from that thrust collar, do some calculations, figure out what your expected thermal growth is, and give yourself a little safety factor there. Okay. Keyphasor pulse requirements. I think it's pretty obvious, but which of these pulses would you rather use, right? I'm going with this one. Narrow pulses, those that are less than 10 microseconds, and you can figure that out by going, what's your RPM and how wide is that compared to the circumference of the shaft. You'll want to have at least 5 volts peak to peak. If you got greater than 10 microseconds, anything greater than 2 volts peak to peak is probably good. Okay. So back when I started, I told you I started back in the Stone Ages. So we had an instrument called the DVF2, Digital Vector Filter 2. And on that instrument, I was able to adjust the threshold for the Keyphasor, as well as the hysteresis. That's all done automatically anymore, but I thought I'd go through it just so you could understand what's going on. So I've got my input signal. I've got a pulse here. It's not a great pulse. There's some vibration on it. Got another pulse. So the first thing that we need to do is make sure that the pulse crosses this threshold. But crossing the threshold itself is not enough, because what if I had something like this, but it was up near the threshold? I'd be going in and out and in and out and getting multiple Keyphasor pulses. So we have this thing called hysteresis. So how much does it have to exceed that threshold by? So it has to exceed it on this side. And when it does, we'll get a trigger in, comes down here at this point, and then it travels back up. It hits the threshold again, but does it trigger now? No, it still needs to go up above that hysteresis level. So that's where it'll hit the trigger out and we'll get our speed pulse. So this will be that. Okay. Again, this is all done automatically anymore, but it's nice to understand how it works. Okay. Now, we've been doing this webinar series for quite a while now, since the beginning of March, probably. And on occasion, we talk about non-standard target materials. So if you've been tuning in, you'll know that when you're using a different material than 4140, you're probably going to want to use a modified proximeter so that you get the correct scale factor. But is that important when you're doing a Keyphasor? It really is, because you're not looking for a value. You're just looking for that pulse. So if it's calibrated, it doesn't matter. So here's a way of determining, do I need a standard prox, standard prox or a modified prox? So first of all, you need to assemble a valid proximeter transducer system. That's going to be a probe, an extension cable, and a proximeter. And then, of course, you got to provide it with power. And when I say a valid proximeter transducer system, I mean, if you're using a 5-meter prox, you want to have a 5-meter extension to cable and probe combination, not a 9-meter. Okay. We're going to measure that proximeter output signal using a DC voltmeter. And the first thing you're going to do is you're going to hold that probe up in the air with it not able to see any target material. And you're going to verify that the proximeter output signal is greater than 20 volts DC. Now, again, if you don't have a proper valid proximeter system, you might not get that. Okay, but as long as it's valid, you should get that. So that's easy. The next thing you're going to do is hold the probe against the target material so it has a 0 gap, and verify that the proximeter output signal is less than 3 volts DC. If you've got that, you're good. There's no need to get a modified prox. Okay. Now, if you've got something like aluminum, it's very transparent. I can imagine that you might not get that 3 volts DC. Okay. But anything that's steel based shouldn't be a problem. So I also want to talk about reciprocating compressor timing. This graph here shows what is the RPM over 1 rotation of the crank. Okay, so you can see it goes from a low of 290 to a high of 302 RPM. And that's because if you think about it, that crankshaft is pushing a piston in and pulling it out. And at different angles of that movement, it's got different loads on it. So when it's really working hard, it's going to slow down. When it eases up and it's not working so hard, it's going to speed up. So when you're doing valve diagnostics, you really need to know where that crank angle is accurately to get the best diagnostics. So what we do is we have a multi-event wheel. It's a bad picture, I'm sorry, but it's got 12 notches. And then it's got a one divided notch. And we set it up so that that divided notch fires when the first throw is at top dead center. If we know that first throw is at top dead center, we can index all the other throws so that we know where they are. Okay, and that gives us much less error in our diagnostics. We also developed a strap-on wheel. This is just made out of sheet metal, laser cut, and I just wanted to show it to you. This one's got offset Keyphasors, got paths for 2 Keyphasors, and here's a double notch there. And here's one that is not offset but is installed in a crank on a crankshaft, just so you see what it looks like. Okay, so that's what I had for single event per revolution Keyphasors. Let's talk a little bit about overspeed. And I'm simplifying this a bit, but this is a fairly short webinar. So rotating machines have several critical speeds. Now, when I started with Bentley, Nevada, and Dr. Bentley was a mentor of mine, if you said critical speed, he'd well, he wouldn't slap you, but he'd let you know that that was a bad term. And that was because people routinely referred to resonant speeds as critical speeds, and they are different. But in this discussion, I'm going to say that critical speeds are accurate. The first one that I want to talk about is yield speed. And speeds above the yield speed can result in catastrophic failure, leading to massive damage and the possibility of injury and or death to personnel. So that is a speed you want to stay away from, right? And that's a speed where the centrifugal force generated by the speed is enough to liberate the rotor components. Okay, so you want to stay away from that speed. Next critical speed is maximum continuous. It's commonly called the rated speed. So in a big steam turbine generator, 3,600 RPM. Let's just say 3,600 is your max continuous. Then you have overspeed trip speed. Okay. Typically, that's going to be 10% greater than max continuous. So in a 3,600 RPM machine, that's 10% is 360. That brings you up to 3,960. And that overspeed trip speed, we want that to be as low as possible to provide time for the overspeed detection to occur. You want to give your instrumentation some time to understand that that trip needs to occur. And it needs to react prior to reaching this temporary overshoot speed. But you don't want that speed to be as low that it's triggered by normal variations in the max continuous. Okay. And then this NOS is maximum temporary overshoot speed. It's got to be less than the yield speed. And typically, you're going to make 10% greater than the overspeed, or about 21% greater than max continuous. And I can't do that math in my head, but it's going to be 3960 plus 10%. So a little bit, say 4260, something like that. Okay. So electronic overspeed systems act to mitigate the risk of an overspeed event. They need to be able to react quickly. So you wouldn't want to tie just a single Keyphasor notch to an overspeed trip mechanism because it can't respond fast enough. You need multiple pulses per revolution to provide a quicker response. Typically, geared wheels are used. So here's a true gear. Here's something like our multi-event wheel that is not a true gear. And then if you have an axial application, you could use this phone dial wheel. And I know there's some people on the call that probably don't know what a phone dial is. Starting to get old. But contact your Bentley Nevada account manager about your specific application. We can certainly help you. Again, these electronic overspeed systems need to be robust to eliminate false. You don't want that machine tripping falsely, but you also don't want to miss any trips either. So typically, we're going to use triple redundant probes. They're going to be either proximity probes or magnetic speed pickups will work fine for this type of application because the faster those pulses go by, the more pulse you get from a magnetic speed pickup. And then we'll do 2 out of 3 voting. So it can't be just one module saying, hey, I think we're at overspeed. We want to have verification. If you just used one, you could have a false trip. So for electronic overspeed, we use the 370155. It is purpose-built for this sort of thing, and it's compact, robust, triple modular redundant, standalone electronic shutdown device. Okay. It is suited for 670, API 670, as well as SIL 3 applications. Has 6 speed inputs, 2 redundant speed inputs per module. I believe these are the input modules. Actually, these are the input modules. I keep doing that. Magnetic pickups or proximity probes. Does have compact inputs and configurable relay outputs with dedicated signal processing. The configuration tool is simple to use. It's graphically oriented as well. And it'll give you 4 to 20 milliamp outputs as well as 12 relay outputs. Okay. Talk a little bit about zero speed. Zero speed measurements can help us prevent several issues like rotor bowing by accurately measuring rotor speed at very low RPMs. And, back when I was doing field balancing, if we had a steam turbine generator, we'd stop it to put the balance weight in. We'd have somebody standing there with a stopwatch. And that person, their sole job was to measure how much time we were off gear. We'd hurry, put the weight in the proper location, and then we'd rotate the shaft 180 degrees. And that same guy with the stopwatch would restart his stopwatch, and when we hit the same time that we had been sitting there before, we'd start the unit on turning gear. Okay. Those rotor bows can become so large that you can't start the unit up. And most large steam turbine generators have an eccentricity probe, which is also used as a measure of the amount of rotor bow. And you have to rotate the shaft until that eccentricity gets below a certain value. So zero speed is typically used on large steam turbines to make sure that the turning gear is in operation. They typically rotate at about 3 to 4 RPM. And zero speed measurements must be made by a Keyphasor probe observing a multi-event wheel, typically the turning gear itself. You couldn't do that with a once per turn notch. It's just not going to give you enough signal input. And engaging the turning gear while the rotor is still coasting down, but still above 3 or 4 RPM, can result in damage to the turning gear system. So the zero or low speed monitoring capabilities of the 3550 TAC are vital to ensuring proper operation. Okay, reverse rotation. This is also an issue where you might have several pumps, and the leaky check valve allows the pressure from all the other pumps to take a pump that isn't operating and push fluid back through it and rotate that pump. Now you go to start that pump, and at best of times when you're at zero speed, you're putting a lot of torque on that. Now you're trying to overcome speed in the opposite direction. It's that much more torque, and you could snap your coupling, or if you have a clutch, do damage to the clutch. So one of the reasons we use reverse rotation. I told you magnetic pickups are great for the overspeed stuff because the faster the projections are going past that probe, the better it responds. They are not allowed for reverse rotation because these things go so slowly. So probe A, let's just say that's your Keyphasor probe, it has to lead probe B. So in this case, we're going counterclockwise. So it hits probe A first, and then probe B ideally should be located 45 degrees afterwards. Has a tolerance of 22.5 degrees, so it could be between 22.5 and 67.5. Okay. Now, what happens if you have multiple events for this? So for every notch of projection, there are that many acceptable positions. So here I've got one notch. I have one acceptable position for probe B. Here I've got two notches, but I've got two locations that the B probe can be in. Here I've got 4, and I've got, again, 4 locations that probe B can be in. But you'll also notice that I went from a 22.5 degree tolerance down to a 6 degree tolerance. So the more points there are, the tighter the placement tolerance has to be. Okay. So rotor acceleration. We know that we've been talking about how many pulses you get. And in a variable speed machine train, you need accurate speed indications throughout their operating range. We prefer to look at a gear to get more events per revolution. Gives us that faster response to small speed changes. The other thing I want to note here is that the 3550 TAC monitor measures rotor acceleration by calculating the change in speed over a given time. And I've had people ask me, John, why do we care about rotor acceleration? And I can only tell you anecdotally that when I went to a plant and they brought the machinery up slowly in a very controlled situation, for whatever reason, those machines really ran very smoothly. I never had any problems with them. But when I went to plants where it was, let's get this machine up and running now, and they obviously had higher rotor acceleration, those machines didn't behave quite as nicely. The other reason is if you have high rotor acceleration, you're going to be putting more stress on the parts, and it just isn't good for the machine. So that's it for rotor acceleration. Hopefully you've learned quite a bit about everything you needed to know about Keyphasors.